what I'm going to talk about is somehow based on work with many people that I'll mention as we go through it. And I would like to start with, as a motivating topic, with something that is close to the heart of many of the people in this audience, namely the goal of categorifying Wedrich and Derived invariants. And also the Wedrich and Derived invariants are invariants of three manifolds, numerical invariants, that arise from the representation categories of quantum groups. And in the easiest possible examples, these numerical invariants can be computed as sums of colored Jones polynomials at a root of unity. So that would be somehow the type of one way in which we could access such three manifold invariants. And now we know from the last 25 plus years that much of quantum group representation theory categorifies. And so, for example, Khovanov taught us how to categorify colored Jones polynomials. And now, well, here's an open problem, very, very famous open problem, namely to categorify the WRT invariants to get homological three-manifold invariants. And a part of our wish list should be that these are computable in terms of the link invariants, just like the ordinary Wedrich and Derived invariants were. And ideally, we would get useful smooth four-manifold invariants by exploiting the functoriality of this construction. Okay, so the approach to this problem that I would like to entertain in this talk goes as follows. So first, we need to understand the conceptual background of Wedrich and Derived invariants via a family of extended topological quantum field theories. So basically, we really have to somehow dig into how WRT invariants arise from the representation theory of quantum groups. And then it turns out that there's just not one TQFT in the background, but there's actually a triple. And two of these TQFTs are determined by what I would like to call local data, so the local TFTs. And then the idea would be to categorify this local data. And of course, categorification is typically not a deterministic process, but something like an art. And we would have different choices for how to do this. And then we would take this categorified local data and try to assemble TQFTs from that. And we could call them categorified TQFTs. The results that we'll get depend on the choices we made in the categorification process. And along the way, we might circumvent some of the finiteness constraints that are imposed when we want to construct WRT invariants, because categorification seems to be a bit more robust. And yeah, so today I want to talk about recent progress along this approach. And I want you to take away two things. So the first is that there exists somehow a first approximation to categorified WRT invariants, which already satisfies like the 2 points on the wish list, namely that they're computable in terms of link homology and that they give a useful smooth four-manifold invariant. And the second thing I'd like to mention and give a bit of an outlook is that there should be a second generation of such categorified TQFTs that really show some hints that we're categorifying WRT invariants. So there's some small hints that come into sight that there's a categorification of WRT in these theories. So that's the plan. We started with this motivation of categorifying WRT invariants. Now I'll have to talk a bit about this TQFT background. This will take roughly half of this talk. And then in the second part, I want to, as the abstract advertised, talk about 4 types of TQFTs that you might expect to arise from categorification. So the second part that we're jumping into right now, this is really building, standing on the shoulders of giants. And I can only give, so this is kind of has a long history, and I'll do my best to somehow do this justice, but obviously I won't be able to do this fully. So let's see, what can we do? So I want to start with this perspective that TQFTs are an assignment that maps spacetimes to algebraic or categorical structures in a way that is compatible with gluing. And so I want to take the perspective that there is a fixed spatial dimension that I'll call n, and secretly we'll also have to choose some tangential structure on our spacetimes. And then we would expect that this extends up and is functorial under, well, at least some n+1 dimensional Bordisms. And today it will be also important that sometimes you can extend this further down than dimension n, and assign some higher algebraic structures to lower dimensional manifolds. And this is useful if you want to glue spacetimes, because you want to cut them along hyperplanes, say, and then you want to compute the TQFT on these pieces separately and then algebraically glue the results. And for that, you need to understand what this TQFT wants to assign to lower dimensional manifolds. So this amounts to some computations of manifold invariance via cut and paste techniques. And I want to use this terminology. I want to call a TQFT local if it extends all the way down to the point and then is determined by what it assigns to this point via all these gluing operations. And just for the record, today all manifolds will be smooth and oriented. So that's my tangential structure that I'm choosing. Good. The most optimistic case, somehow the best case scenario for an n+1 dimensional TQFT will assign vector spaces to n manifolds, to closed n manifolds. And then in this best case scenario, we have an extension up, and to closed n+1 dimensional manifolds, we want to assign numbers, and to n+1 dimensional Bordisms, we want to assign linear maps, and we all know this story very well. And then we'll try to extend downwards. We want to assign categories to n-1 manifolds, and then we're not satisfied with this. We want to go even further down. And then, well, we go all the way down to the point, or to 0 manifolds, and we want to assign n categories to them, and you can do kind of the pattern matching, and somewhere in between you assign k categories. Okay, so this sort of picture ignores many important aspects. I'm completely ignoring what sort of ambient symmetric monoidal higher category we should work in which these n categories are objects. We're completely ignoring what the values would be on manifolds with boundary, so that we could glue them. And then we need, of course, manifolds with corners and so on. I'm ignoring dualizability issues, including somehow the strong finiteness conditions that are imposed on these n categories if you want to extend all the way up to n+1 manifolds. And I'm ignoring the dependence on the tangential structures, which are some sort of pivotality conditions on these categories. So all of this is somehow blurred out at the moment. Now, let's do a case study of 3 different types of TQFTs which are relevant in this story and which are related, which can be constructed from the representation theory of quantum groups. And the first family of examples are the TQFTs of derived Vero type. So these are local, so extending down to the point, 2+1 dimensional TQFTs. So they assign numbers to 3 manifolds. These are the derived Vero invariants. They can be constructed from a spherical fusion category. This is a special type of monoidal category with very nice properties so that you have a string diagram calculus that works on the 2-sphere. And then somewhere in the middle, you can also describe what these TFTs assign to, well, surfaces on 1 manifolds, and there's certain skein modules. So for example, if you have a surface, you can use the string diagram calculus of the spherical fusion category to describe like a vector space of string diagrams drawn on the surface. And that will be closely related to what this TQFT assigns to the surface. Okay, and then there are, so I tried to list some of the relevant work, certainly not all, if you want to have a look at the slides later. Second type is the so-called Crane-Yetter type family of local 3+1 dimensional TQFTs. So we're 1 dimension higher. Here we assign numbers to closed 4 manifolds, vector spaces to closed 3 manifolds, and then, well, these top dimensional numerical invariants are called the Crane-Yetter invariants. This construction works if you start with a so-called ribbon fusion category. That's now not a monoidal category, but even a braided monoidal category with very good properties and additional structure. that is somehow sufficiently finite to go all the way up to 4 manifolds. And again, for the invariants in between, so for example, for 3 manifolds and for surfaces, it's possible to describe the values of these TQFTs as some sort of skein modules. And this time, these vector spaces can be described as skein modules spanned by embedded ribbon graphs in a 3 manifold. And we use the graphical calculus of this ribbon fusion category to somehow globalize and obtain these manifold invariants in the intermediate dimensions. One caveat here is that these Granietta invariants of 4 manifolds typically don't see much of the topology of the 4 manifold. They only depend on Euler characteristic and signature. So they're not really interesting 4 manifolds in themselves. But there's a closely related theory, which are the Reshetik and Derived TFT. So this is now the third member of the triple. And this is what I call a 1, 2, 3-dimensional TQFT. So it's not of the local type, but it assigns things to 3 manifolds, 2 manifolds, and 1 manifold. To 3 manifolds, it assigns the WRT numerical invariance. The construction can be done from a modular, starting from a modular fusion category, which we can interpret as what this TFT assigns to the circle. And then there's the slogan that this Reshetik and Derived TFT is not a local TFT, probably. It does not extend down to the point, but it can be understood as a boundary theory for this Granietta TFT from the previous slide. And this is an idea that I've learned from Kevin Walker, and then this concept of a boundary theory was formalized by Fried and Telemann and Johnson, Frey, Scheinbauer. And this is a really active area of research itself. So for example, like 2 days ago, there was a paper by Benjamin Hayoum on the archive. Anna. Is it easy to explain why it's not local? Well, so for example, if you believe that this is a boundary theory for Granietta, as I do, then it would be really natural to obtain, if you want to go as far down as possible, you would want to evaluate Granietta on an interval. And so you could, on the boundary of that, you would see 2 points. And so this TFT basically can assign something to 2 points, but not to 1 point. That's my naive understanding, but maybe you have. I think you have to press the button if other people should. That's fine? Okay, we'll talk later. Okay, now, how can I convince you? So what is a basic instance of this boundary thing? Chris, do you have a question?
Maybe this is not. I did press the button. Okay. Can anything anomalous extend down to a point? I mean, like you have this dependence on something which is apparently coming from some 3-manifold, or you know what I mean? So I don't know if could that ever happen?
I don't know. I think we need to think about it.
Okay.
Okay. So, but yeah, Tom.
Ended on essentially a conformal structure on the surface. Not the vector space isn't functorial in the surface. You need the conformal structure to actually construct the vector space.
So I intentionally left out the vector space thing here.
Yeah, okay.
So I'm sorry. I really have to somehow take a very coarse-grained view on these theories. And I want to somehow use this as a motivation to somehow get to the point where I can say something about the categorified picture. But yes, I think these are all valid questions. Absolutely. Okay, so what's a basic thing? So when we compute Whitney-Reshetik and Derived invariants as sums of colored-Jones polynomials, what is actually somehow going on in the background is that we often somehow use a surgery description for the 3-manifold. So we explicitly write the 3-manifold as the boundary of a 4-dimensional surgery cobordism, say from the empty manifold to the 3-manifold, but then let's turn it around and let's think about it as going from the 3-manifold to empty. And now the Granietta invariant will assign to that 3-manifold some sort of a skein module, which has a distinguished element, and it's called the vacuum skein. So it's the empty skein module, this empty skein in the skein module. And now the 4-manifold gives us a map that we can evaluate on this vector to produce a number. And then up to some scalar normalization, this value does not depend on the 4-manifold, on the surgery cobordism that we chose. And well, it will only depend on Euler characteristic and signature of this cobordism, and that can be renormalized away, and that number then recovers this Wedrich and Derived invariant. Okay, and then there's one other relationship that will be important somehow motivationally, and that is that if we start with this ribbon fusion category that we use to build the Cranietta thing, then on the boundary, we see Wedrich and Derived on one hand, but on the other hand, we could forget the braiding of this ribbon fusion category and get something that we can feed into this Derived Vero machinery. And then there's a relationship between the corresponding 3-manifold invariants, namely the Derived Vero invariant is the norm squared of the WRT invariant. And that's something that we might also see today again. Okay, so what are the takeaways of these 3 case studies? So quantum group representation theory gives a family of TQFT triples, a local 3-dimensional theory, Derived Vero, a local 4-dimensional theory, Cranietta, and the boundary theory, this Wedrich and Derived 1, 2, 3-dimensional TQFT. Then this top-dimensional invariants in Derived Vero and Cranietta very much depend on finiteness conditions of these local input data categories. So in the case of quantum group representation theory, we have to specialize Q to a root of unity, and then semi-simplify what we get. And then one can then somehow, the state sums converge, and then we have this extension to the top dimension. But we've already observed that somehow the lower dimensional levels of these TQFTs can be described via skein modules, and this is somehow a slightly more robust kind of construction that does not require going to roots of unity or semi-simplicity. And in that case, we still get something that we can call TQFTs, although they don't go up to the top dimension, and I like to call them n plus epsilon dimensional TQFTs. So they assign vector spaces to n manifolds. Diffeomorphisms of n manifolds somehow still act as automorphisms of these vector spaces. These theories are local, so they extend down to the point, but maybe not up. And they might be even more partially defined. And this n plus epsilon dimensional TQFT concept is also something that I've learned from Kevin Walker. Side note, not extending up to the top dimension might actually be a very useful feature for certain applications. So for example, there are some 3 plus epsilon dimensional TQFT, so 3-dimensional skein theories if you want, that can be extended to some 4 manifolds, but only those that can be presented as 4-dimensional 2-handle bodies. And Anna Belyakova with Bobcheva, Derenzi, and Piergalini has a very nice paper about this from 2 years ago, which characterizes algebraically such TFTs that extend to 42-handle bodies, amongst other things. And now one could hope that if one can find such an example of a TQFT that does not extend to 4-dimensional 3-handle bodies, so basically it stops at the level of 42-handle bodies, then this TQFT might detect counterexamples to a 4-dimensional analog of this Andrews-Curtis conjecture that we've heard about yesterday. Because then the 4-manifold invariants that this will compute will be manifestly invariant of 4-dimensional 2-handle bodies, but maybe not of 4 manifolds up to Diffeo. Okay. Now, having thought about these relationships of WRT invariants to Derived Vero and Cranietta invariants, one might get the impression that categorified WRT invariants might need or might be related to categorified Cranietta or categorified Derived Vero invariants. And now this opens up a strategy for using skein theory to extract, well, parts of these theories without having to think about roots of unity, semi-simplifications, state sums, and so on, namely by focusing on the lower dimensional strata, on the lower dimensional values of these TQFTs. So the idea is that categorification and skein theory should give access to categorified versions of Krian-Jetta invariants in dimension less or equal to 4. So this wants to be a 5-dimensional theory, but it might not extend to all 5 manifolds, but we can try to understand it on up to 4 manifolds. And analogously, there should be a categorified derived zero-type family of TQFTs that we can skein theoretically access up to manifolds of dimension 3. Now, where does this come from? So this idea is somehow inspired by the periodic table of n categories. This is something that arose in around the same time as the cobordism hypothesis was proposed by Byers and Dolan, which was then proven by Lurie. And these TQFTs, these local TQFTs, of which derived zero and Krian-Jettas are examples, are completely controlled by certain higher categories. And they fit somehow can be categorized somehow in this table. And the way to read this table is that the columns are parameterized by categorical dimension. So in the column labeled 1, let's see if I can, in the column labeled 1, I see categories. In the column labeled 2, I see certain 2 categories. Well, then I can extrapolate to the left, and in the 0 column, I see 0 categories. And then the rows somehow express a degree of monoidality. So E1 means I look at monoidal things, at things that have an associative unital multiplication. In the row labeled E2, I see things that come with a braiding, so a way of comparing the 2 ways of multiplying 2 things. And then this can be extended up, so E0 means I look at pointed things. E3 is something that we're maybe not so used to. And then we can place monoidal categories and braided monoidal categories that give rise to these derived zero and Krian-Jetta theories into this table. So they appear here and here. And using categorification is for me a process that takes often sets to categories, categories to 2 categories. So in some sense moves 1 click to the right in this table. So if we want to look for categorified derived zero and categorified Krian-Jetta invariants, my proposal would be to look for monoidal 2 categories and to braided 2 categories as local data. What sort of TQFTs do we expect to get from this? Well, the formula is the dimension n for the n plus epsilon dimensional TQFT that I expect is computed as the sum of the category level and the degree of commutativity, the degree of monoidality. So basically, the dimension of the TQFTs in this table increase as you somehow go along parallels of this anti-diagonal. So the things in the same color have the same dimension. Okay, and well, this is, so I was talking about skein modules and skein theory and wanted to propose this as a nice way of accessing the lower dimensional strata of these TQFTs. And this table also tells us what sort of skeins we have to look at. So in derived zero and Krian-Jetta, we know that we look at string diagrams, diagrammatic calculus in 2D or in 3D, which you see in the middle column here. And then, in the categorified versions, we would look at surfaces in 3D or in 4D. So these will be skein theories based on surfaces typically. Now, if you're a 4-manifold topologist, and I guess to some degree we all are, and yesterday we heard nice talks about this, somehow it's an interesting way of studying 4-manifolds is to look at embedded smooth surfaces. And so, in some sense, if you have a skein theory for smooth surfaces in 4-manifolds, that could be a nice receptacle or a nice way of probing 4-manifold topology. Okay, so this was the first part of this talk, so basically case study and setting up what we want to do. And now I want to start proposing 4 types of TQFTs that you could expect to come out of categorification. But before going there, I wanted to ask if you have questions.
You can expect that things are only things are only partially defined in the top dimension? Is there any setting where things are only partially defined in lower dimensions as well, like a 3D TQFT where you get it?
You could definitely have that. So yes, so we will completely ignore the top dimension for most of what's going to happen. And yes, you could also imagine that you have TQFTs that basically start at the point. They want to be 5-dimensional, but then they also only go up to, I don't know, some 2-manifolds, some 3-manifolds. So kind of there are various notions of, I don't know, being partially defined that show up in practice. Yes. 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 I mean, you should be able to.
Which button? Like you had these 3 examples. So where are they at the table? And could you comment a little bit?
Yes, thanks, absolutely. Okay, so the derived zero thing lives here. Yeah, it's based on a very special type of monoidal category. Okay, so really in the middle. The Crane-Yetta thing, where's my pointer? The Crane-Yetta thing lives in the braided cat box. Okay, so one step below. My point is that WRT you won't find in this table because it's naturally, or at least as far as we understand, it's naturally a boundary theory of the Crane-Yetta thing, which is in this slightly orange box. Okay. Yes. So I'll go there again in a second. Are there more questions at this point? No. Okay. So let's pick up your question again. So here it is. And now we kind of, I'm specializing a bit more. So instead of saying E1, I say monoidal, and instead of E2, I say braided. And then, well, it's topological quantum field theories. We're typically in a linear setting. So derived zero and Crane-Yetta are based on linear monoidal categories and linear braided monoidal categories. And you hear, I think this now visually answers your question too. And what could we expect from categorification? So we would go one step to the right. We'd look for certain monoidal 2 categories or braided 2 categories. And of course, we want them to be linear in some setting. And here I say locally linear. So I mean linear at the top morphism level. And turns out that there is already some sort of skein theory TQFT that exists in the literature and has done so for a while that fits into this box to the right of derived zero. And I call this the Asaeda-Frohman-Kaiser TQFT. And this is based on skein modules of certain decorated surfaces in 3 manifolds. They call them Barnard-Hahn skein modules because they're often built on the skein theory of dotted cobordisms that appear in Barnard-Hahn's description of Khovanov homology. Okay, honorable mention here are the Douglas-Reuter invariants. So one can interpret this as a 3 plus epsilon dimensional TQFT whose 3-manifold invariants are skein modules generated by certain foams embedded in 3D. And these foams are labeled by data coming from a so-called fusion 2 category. And the whole point of that construction is that this really extends to 4D by some state sum construction. But then David also proved that probably they don't detect exotica, at least in this oriented setting, because these TQFTs are too semi-simple in some sense. Next thing, so there are also locally linear 2 categories that one can get from categorification. And they give rise to skein modules of surfaces in 4D. And well, in some sense, inventing a skein theory is very easy, right? You say what sort of skeins you allow, and then you invent some skein relations. And what will typically happen is that either your skein modules are way too large because you chose too few skein relations, or your skein modules will be 0 because you've picked inconsistent skein relations, right? And so the art is somehow to pick a reasonable set of skein relations. And the way you can get a reasonable system of skein relations is to look at link homology theories, which are functorial under cobordisms. And so in this paper with Morrison and Walker, we did this based on the functorial GLN Khovanov-Rosansky link homologies, which categorify the quantum link invariants associated to GLN. Now, you can do something else. You can try to appreciate that these link homology theories are homology theories, so they're always computed via chain complexes. And maybe if you're really optimistic, you might think that one could do most of these constructions on the chain level. So then one leaves the setting of linear, locally linear two categories, but one has to work with a much more complicated gadget, namely some sort of infinity two categories, which are not locally linear anymore, but stable. So locally stable infinity categories. Now, this is somehow a story that's very much on the development. At the moment, somehow we see some traces of the local data that one would want to assign to the point in such theories. And we hope that at some point this can be extended to give somehow derived skein modules for surfaces in four manifolds. And the one prototypical example where we have such a locally stable braided infinity two category appears in a paper with Liu, Meselji, Reuter, and Stroppel from last year. And the braiding here is constructed on categories of chain complexes of circle pi modules with a braiding given by Rouquier complexes. And now it's an empirical fact that somehow most quantum link homology theories have something to do with Rouquier complexes. So they somehow factor through, or we expect that they factor through this construction. Okay, and then filling the table, there should also be kind of a derived version of this Asaeda-Frohman-Kaiser TQFT. So this we started to explore in a paper with Matt Hogenkamp and David Rose last year. And this is supposed to be some kind of prototype derived skein module theory for surfaces in 3D. And in that case, we see, well, some relations to known link homology invariants, namely the Rosansky-Willis invariants for links and connect sums of S1 times S2s. And there is a known relationship to stable WRT invariants, which are some version of WRT invariants which are defined for manifolds where you, with certain types of manifolds where you don't need to pick a root of unity. So that's kind of the four different types that I want to talk about, but Chris has a question. It's subtle. It's really subtle because, so I'll come to that. I'll pick up this point. The thing is that you take, so in the end, theory 3 wants to assign chain complexes to four manifolds, but the invariant, this will only be an invariant up to quasi-isomorphism or coherent higher homotopy. And so in the end, if you want to get some concrete vector space, you'll have to take homology. And in the theory 2, you take homology extremely early. You take homology basically locally, and then you assemble the whole thing. So they won't be related directly. More questions? OK, so plan for the rest of the talk is to look at kind of, to survey what little is known about these four things. Okay, first, this Asaeda-Frohman-Kaiser type TQFT. So here, the local data, the thing that I want to assign to a point, is a locally linear monoidal 2 category. And there's kind of various ways one can construct these things. And a really nice one is if you start with the commutative Frobenius algebra, which controls a classical 2-dimensional TQFT. So it assigns vector spaces to circles and linear maps to pairs of pans and so on and so on. And one example that probably everyone knows here is the Khovanov-Banatan skein theory, which is based on dotted coboidisms. Yeah. But there are more things one can choose. So for example, if one has a closed foam evaluation formula, for example, the one that Christian Blanchet gives in his model for oriented Khovanov homology, that would be a valid choice. Or Robert and Wagner have a foam evaluation formula controlling the foam categories that appear in combinatorial descriptions of Khovanov-Rosansky GLN homology that we could use here. Or we could use other foam theories. For example, the ones that Khovanov and Robert developed, inspired by Kronheimer and Mrówka's work on kind of approaches to the four-color theorem using gauge theory. So these are all valid choices. I don't think much of this has been explored, but they're kind of natural choices for constructing such locally linear monoidal 2 categories. So you would expect some 3 plus epsilon dimensional TQFTs being built from that. What would you get? So for an oriented 3 manifold, you would build a skein module of decorated surfaces or foams in the 3 manifold, and then you mod out by isotopy and local relations, which are governed by this monoidal 2 category. And then you can extend this down. So for a surface, you would assign a linear category whose morphism spaces you would compute as values of the TQFT on surface times interval. And these things, based on the Barnard-Hahn skein theory, for example, are already heavily used. So for example, if you want to understand the Asaeda-Frohman-Kaiser version of Khovanov homology for links in thickened surfaces, then Jeffrey Berner gave a description of this invariant in terms of these categories that the Asaeda-Frohman-Kaiser TQFT assigns to the surfaces. And another thing that you can observe here is that these theories can really directly categorify skein modules based on the temporally leap category. So this is also something that we see in Khovanov homology and categorification literature in many places. So these things appear. Now, side note, there's kind of lots of things that one can use to build such monoidal 2 categories, and one can try to tweak this construction. And so my grad student, Leon Gertz and Kevin Walker, they both have versions of such linear monoidal 2 categories given rise to 3D skein theories, which extend to 41 handle bodies. That's pretty easy to achieve. And then they extend a little bit higher up to 42 handle bodies. And if one tweaks the parameters correctly, then one can arrange that these do not extend to 43 handle bodies. This could be interesting in this Andrews-Curtis context. Okay, that's what I had to say about this type of TQFT, basically as a warm-up. The next one, we go one step down in this periodic table, and we look at locally linear braided 2 categories. Now here, we would get a 4 plus epsilon dimensional TQFT, and the constructions that we have somehow start from link homology. And we cannot use any type of link homology. We have to have some additional properties. So it needs to be functorial in the 3 ball. So link cobordism in B3 times I have to induce linear maps in a well-defined way. The theory has to be monoidal. So if I, for example, include 2 3 balls in a bigger 3 ball, I need the construction to respect this and map this disjoint union operation to tensor products in the correct way. So the technical way of saying this is that we need an E3 monoidal. We need kind of the link homology functor to be E3 monoidal. And then we need something else. We need that there's some sort of a sphericality property that allows us to extend, so to see that the link homology is not intrinsically defined for links in B3, but actually in S3. So with these three things sorted, one can build a skein module of decorated smooth surfaces in any oriented 4 manifold. And here's a picture that I took from our paper where we describe the skein relations. So the skeins are these diagrams. You can interpret them as being smooth oriented surfaces inside the 4 manifold, which then end on some small balls that we've drilled out of the 4 manifold. Or you could also think about this as being somehow surfaces in the 4 manifold with some prescribed singularities. And then the links that you see on these input balls correspond to the links of these singularities. These have to be decorated by algebraic data. These are these vectors vi that you might see in the picture. And this algebraic data is supplied by the link homology theory. And then the skein relation says that I can somehow cut out some pieces and replace the algebraic data and update the algebraic data in a certain way. This is the typical way in which skein relations work. You have local relations, which are somehow governed by differences of local configurations that your categorical data could not see. And here it's just a bit more complicated because we have to draw surfaces in 4 manifolds. Okay, then, question?
Is there a way to replace free spherical by something else to make it work?
Well, three spherical is something that I use in an informal way. Precisely understanding what's needed here is totally open, I think. In particular, you could imagine to run such constructions using other tangential structures than orientation, and then your requirements on the link homology would change drastically. Yeah. Now, this is just kind of the only example that we have access to at the that I have access to at the moment. Okay, going one step down to three manifolds, we expect that one can assign linear categories with morphism spaces, again computed from what the four manifold invariant assigns to M3 times interval. And then you can ask them, what's the relationship to the link homology that we started with? And the answer is that, well, if you look at what the invariant of the four ball is, and this is not, so four ball is a manifold with boundaries, so it really doesn't, I haven't really talked about this yet. But on the boundary, you can specify a boundary condition. And a valid boundary condition would be a link. And if you supply this link as a boundary condition, then the skein module of the four ball with the link as a boundary condition will recover you the link homology. And the whole construction is set up in a way that this is true. So in some sense, this sort of construction changes perspective slightly. The link homology is not an invariant of links in a three manifold, but rather it's an invariant of a four manifold whose boundary is then decorated by the link. Okay, so we set up these skein modules in 2019, and of course the definition as a skein module suggests that this might be very, very hard to compute, and it was a bit hopeless, and there was COVID and so on. And then one day I was extremely happy because Ciprian Manuelescu and Ikshun Nathalat wrote a really cool paper where they show that one can actually compute these things, or at least one can get a recipe for computing these things. So they set up a way of understanding how these skein modules change if you attach or detach a two handle. And then we had a collaborative project with Ciprian and with Kevin Walker where we show that, in fact, these skein modules can be computed along a handle decomposition. Basically, you remove handles somehow from the top index to the bottom, and there's a kind of algebraic recipe what you have to do. And then in the end, this determines an invariance of zero handles, so the disjoint union of four balls. And well, just saw that somehow the invariant of the four ball is just the link homology itself. So the result says then that these skein modules can be computed, in principle, by just understanding the link homology in the three sphere once you have a handle decomposition. This comes with the caveat that this is typically a computation that involves a countable number of steps, and it's tricky, but it's actually surprisingly useful. Okay, and sort of a corollary, or a theorem because you have to do some other things to get there, appears in a paper with Matt Hogenkamp and David Rose, where we show that the Khovanov homology skein module, so this is now based on the GL2 homology, which coincides with Khovanov homology, applied to a surgery cobordism specified by a framed link is somehow an explicit colimit of colored Khovanov homologies. And this is now something that should rhyme with this description of WRT invariants as sums of colored Jones polynomials, except that you have to do Khovanov homology in the colored version, and the sum turns into a colimit. Okay, so this looks somewhat similar. Okay, and now somehow my first goal in this talk was to convince you that even the approximation to these categorified WRT invariants satisfied two items on the wish list, and one was that somehow it can be reduced to link homology in the three sphere, and the second thing was that it's hopefully useful. And so I put a computability check mark here. I'll justify that a little bit more, but here we see it can be reduced to link homology in the three sphere.
Like, do you think you could maybe possibly move the three sphericality?
Probably. I'm not sure this would give a local TQFT. So I mean, I'm super interested in these sorts of questions, but I don't understand what's going on. Very good.
What's the current status? Is it known is for, say, Poincare sphere and minus Poincare sphere?
I don't know. I don't know what the answer is. I'm looking. Some things are known. So in the paper where Ciprian and Ikshu set up this two-handle formula, they observed that the invariants of CP2 and CP2 bar are different. And that somehow, well, that says that the invariant is somehow dependent on the orientation, which is somehow one thing that makes one optimistic. The next thing was that Sullivan and Zhang proved that the invariant of S2 times S2 vanishes. That's also something that makes one, optimistic. Morrison, Walker, and I then wrote a paper where we look at deformations. So not only for the GLN homology theory are there these gain modules, but there are also these Lie and Gornick type deformations. And well, what one can observe is that the GLN gain modules can be deformed, and then one gets something like gain modules based on a link homology theory, which is the direct sum, in some sense, of GLNI link homologies for smaller ni. And that, using kind of paralleling the Rasmussen S invariant, gives rise to genus bounds for smooth surfaces in oriented 4 manifolds. And a particular example you get when you start with kind of the Khovanov GL2 gain modules and deform them into the Lie version, which I like to think of as the GL1 plus GL1 version. And then Wren and Willis wrote an absolutely spectacular paper, at least to me, where they show that these Lie gain modules and really carefully understanding the quantum filtrations on them enable them to extract S invariants for smooth surfaces in a given second homology class in 4 manifolds, possibly also with a link on the boundary. And they prove certain vanishing results for Khovanov's gain modules. For example, for a knot traces where the knot has high framing. And then these vanishing results are inherited on their embeddings, which is somehow a natural feature for gain modules. And then they show that, well, this S invariant and the Lie version and the Khovanov version of the gain module can detect exotica. And in some sense, this is a purely algebra combinatorial way of doing this. So I put a check mark at applications. I heard that this collaboration was really supported by a conference that this Simons collaboration organized in Stanford. So I saw some acknowledgments. So I think this is a really cool outcome. I was pretty blown away by this result. Okay, now so basically 2 items on the wish list. Are at least partially satisfied. But there's one thing that somehow one caveat, and one is that somehow these gain modules do not categorify WRT invariants. So now we have to think about this. Now, in this paper where we show that these gain modules can be computed along a handle decomposition, we also show that for one-handle bodies, 41 handle bodies, these Khovanov's gain modules can be infinite dimensional. So if you look at the dimension, you don't get a number. So in some sense, these gain modules don't even have a decategorification. They're well-defined invariants, but they're not categorifications of anything. And, well, I could say something about the proof outline. Basically, the idea is if you're in B3 times S1, and you look at a tangle with a certain number of endpoints, you can look at the rotation surface generated by that. And these are often linearly independent and of degree 0. And so in degree 0, you then have an infinite dimensional piece. And so that's a sort of, you could think about this as a feature or as a defect of this theory, but it's interesting to understand why this happens. And the idea is that somehow the tangle invariant, before you spin it, is of course a chain complex built out of kind of certain chain groups, and as you trace this out, you would expect that this decategorifies somehow to its Euler characteristic. Yet it doesn't do it here because you've taken homology too early. So there's basically only one way to remedy this and to restore that chain complex is decategorified to the Euler characteristic under tracing, and that is to work with DG categories instead of homotopy categories. So we have to work with the chain complexes directly instead of link homology. And if you run kind of what caused the problem here, if you run this with chain complexes instead of the homologies instead, you exactly recover instances of Rosansky's link homology theory for links in S1 times S2, which were extended by Mike Willis to connect sums of S1 times S2. So basically, the skein modules fail to be locally finite dimensional here. And if we work with chain complexes instead, we know this will be remedied. Okay, so now the downside is that if you want to work with chain complexes, then the local data gets a lot more complicated. We would have to work with a braided two-category for chain complexes. So what is this formally? It's kind of a locally stable E2 monoidal infinity two category. We want this to be related to the chain complexes that appear in link homology. As this E2 monoidal infinity 2 category should be thought of as an object in a certain symmetric monoidal infinity 5 category, and to be able to integrate this to 4 manifolds, we want this to be 4 dualizable. And if we want to do this for oriented 4 manifolds, then this has to be equipped with the so-called SO4 homotopy fixed point structure. This is stuff that the structured versions of the cobordism hypothesis tell us. The dualizability we might get if this category is somehow generated in a sense by 2 dualizable objects, which we interpret as the colors that you can put on the link if you want to do colored link homology, say. Now, there's a prototype of such an object, an object that partially satisfies these requirements in the paper that I've mentioned, where we assemble chain complexes of circle bimodules into such a locally stable E2 monoidal infinity 2 category, where the braiding is given by Roquier complexes. And one important thing to notice is that this is not the final thing that we want, because the objects are not dualizable. So this is reflected in the fact that we can only capture braid invariants here, no tangle invariants, and no general cobordisms between them. But this is sort of the theory that underlies the triply graded homology locally. And we might hope that continuing along this direction, we could build a GLN version for which we would have this generated by 2 dualizable objects, and then also exhibit the necessary pivotality structure to integrate this to oriented 4 manifolds. And well, then this globalization procedure cannot be a skein construction per se anymore, but it has to be some derived version. And there are various tools that are being developed in this direction that go under the name of factorization homology. Now, this is really hard. At least for me, this is really hard. This requires somehow expertise from many different areas. And kind of lots of people are working on pieces of this story. And so, there's a question, yeah?
Invariant of 4 manifolds which happen to be interval bundles in some way? So
this rhymes with your previous question, and maybe.
Okay.
Okay, so basically, while all of this is somehow progressing, I wanted to do something easier, and that's what we do in this work with Hogenkamp and Rose. Why is this easier? Well, because we don't need a braiding if we're in this box of the table. And so the output of this 4th type of TQFT should be a kind of derived version of the 3 plus epsilon of the 3 plus epsilon dimensional Asaeda-Frohman-Kaiser TQFT. And to me, it feels like this is at the right categorical level to parallel bordered suture-Jaeger-Fleur homology. So this is stuff that we're trying to figure out how connected these things are. What we want is chain complexes for 3 manifolds, interpreted as derived skein modules, and we want DG categories for surfaces. The local data should be, okay, and here comes the catch, a locally linear monoidal 2 category. So the same thing that we fed into this Asaeda-Frohman-Kaiser TQFT. Basically, I'm looking at a naive local data, and the only thing that I want to change is the way in which this is glued up. I don't want to glue this up naively by quotienting by skein relations, but I want to glue this up in a derived way. So the skein theory in the 3-ball should be the same as in the previous theory. It's just changing the globalization. And And so the idea is that every oriented three manifold arises from gluing three balls together. And now we do this gluing in a derived way as derived tensor products instead of ordinary tensor products. So for this, we need to understand what to assign to the surfaces that we glue these three balls along. So we need access to the surface invariant. And the surface invariant should come from understanding the three manifold invariant on surface times interval. And now it looks all very circular, but you can actually set this up so that it's not circular by going one index of handle at a time. And OK, I skipped this. And at the moment, we're understanding parts of the surface invariants. And we're currently actively working on the three manifold invariant. So as a theorem, so for a marked surface, so this is a certain technical thing, we can assign a DG category. This has this homotopy category, the thing that appears in the Asaeda-Frohman-Kaiser TQFT, and categorifies the Temple-Liebsky module. It can be computed from every two-dimensional one-handle body structure. It carries the coherent action of the diffeomorphism group. The graded Hom complexes have locally finite dimensional cohomology because they're Rosansky-Willis invariants. And this is somehow the second thing that I wanted to mention here, we see some WRT decategorification here. Because the Hom pairing categorifies these natural Hermitian pairings that we see in three instances in the Turaya-Viro theory, in the Cranietto theory, and also in the WRT theory. And then another interesting categorification gadget makes an appearance, namely the categorified Jones-Wenzel projectors, which were assembled by Cooper and Krushkol into spin networks. And they give somehow an orthogonal generating set of objects in these DG categories. OK, so I'm approaching the end of the time. I'm sorry. Here's only a summary slide. So in the beginning, I wanted to somehow present WRT as a boundary of Cranietta, and as a square root of Turaya-Viro. And these two ideas can guide categorification. The lower dimensional layers of these TQFTs should be accessible using skein theory. We're starting to see two candidate categorified theories of the Cranietta and of the Turaya-Viro type. And the two versions are a linear version and a chain complex derived stable version. This first generation of linear skein theories is starting to see applications, and they become a little bit more computable than you might imagine at first. And the second generation of derived theories is expected to have a better decategorification behavior, but it's extremely challenging. It needs expertise from many directions. This is not something that kind of small teams can do on their own. This is exactly the sort of problem that needs collaborations like these, and I'm incredibly grateful that that this collaboration has existed in the last few years, and I think lots of people have profited from that. Thank you very much.